Morning. We're going to get started at 7 o'clock. So we're going to go over rooftop today, rooftop training. In questions, if you have any questions along the way, just let me know. Can you hear me out there? I hope this is coming through okay. So with that, we'll get started. I see Sean jumped on. Can you hear me, Sean? All right. Today is, we're going to talk about precedent, and we're going to talk about Voyager. And there's another model called Foundation, which we'll touch on just briefly. But basically, the rooftops that we're working with today are Precedent and Voyager. And the Precedent is our 3 through 10 ton units, which is the unit on the left here. And Voyager is our 12.5 through 25 ton. They also make Voyager up to 50 ton units, but at Larson Company, we only handle up to the 25 ton models. The Precedent model can come in electromechanical controls or Reliatel, and that's changing. There's some new controls that are being introduced right now. I don't have any information on them as of yet, but I will as they, as they're released. We'll make sure you guys get all that information. And then the Voyagers are 12.5 through 25 ton, and that is basically just Reliatel at this point. We also have another model called Foundation, and Foundation is our 12.5 through 25 ton models that are pretty basic, pretty simple. It's like a Voyager with Precedent electromechanical controls. Doesn't have anything fancy on it, just basic, transformer contactors, ignition board, nothing fancy about them at all. They also come with tubular heat exchangers. The reference material that comes with the unit are the IOM, the installation, operation, and maintenance. Service facts are being phased out. They're all being incorporated into this installation book. But there's a book called Reliatel, and if anybody needs that book, shoot me an email or shoot me a message, and I'll make sure I send this out in a PDF format. But the Reliatel book is everything that you need to work on these units. It's about a 200-page manual, and it's got all the information to set up the operation. It's not found in the installation book, so if you need that, again, give me a call. We'll get that out to you. All right, Reliatel it's the name of the system that we're currently using on the rooftop. And what it does is you can add or take out boards and configure the unit to do different things. Basically, the RTRM is your main module, and then we can add gas heat modules. We can add economizer modules. We can add input-output modules for, like in the RTOM, for flame or for smoke detectors, free stats, that kind of thing. And then we can also add COM4 interfaces, COM3, COM4 interfaces. We can put in lawn talk boards, backnet boards. The nice thing with the system is the RTRM is the main control, and you can add or remove these boards, and the board will reconfigure itself to recognize the different inputs and outputs on the system. Basically, anytime you add or take out a board and you turn the power back on, this board, the RTRM, reconfigures itself, and it will operate accordingly. So if it sees one compressor, it'll operate as a single stage unit. If it sees two compressors, it'll operate as a two-stage. If it sees an economizer, it'll add the economizer. If it sees gas heat, it will add the gas heat. Um, the nice thing with that is one board fits all units. So you can use a board that would fit a 310 unit, put it on a 2510 unit, and it will configure itself to operate that unit accordingly. Okay, so with that being said, we'll get into some of there's some quirks with the systems that you need to be aware of if you're working on them. We've got some snubber circuits built into our controls, and basically what this does is it puts a resistor and a capacitor in parallel with the contacts to reduce inrush current. And what that does is that prolongs the contact life on the board, but it also can throw some signals out to the system that can send you in the wrong direction if you're not aware of them. So what this does is when the load is connected, the load basically absorbs that little trickle voltage that goes through this circuit. But when you disconnect the load, what you're going to get is a phantom signal. So as soon as you disconnect the load, it's going to send 25 volts out on this wire. And you're going to read 24 volts, and it may not be a closed circuit. It may just be this phantom voltage, trickling through this circuit. So when you're checking voltage on these units, make sure the load is connected, and it won't give you some false readings if you're aware of this particular circuit in there. And it's on a lot of the circuits. So if you unplug a compressor contactor or fan contactor, you may see phantom voltage there that is going to give you some false readings. So, just be aware of that. Now, on the board, are 1 through 14, and then there's a RWGY, and there's a hierarchy of controls on how this works. So, number one is if you have a Lontok card or a TCI 3 card or a TCI 4 card connected, that's priority 1. So when you have a communication card connected, these terminals don't work. They're deactivated at that point. Okay. So if you have a Lontok card in and you try to jump out R to Y or R to G, it's not going to do anything. It's going to ignore these inputs and go with the initial input. So if you want to jump out a unit, you have to disconnect the COM3 or COM4 card. Okay, that's priority 1 or hierarchy 1 on this one. The second one is this 1 through 5. So if you have wires on 1 through 5, this is a 5-volt DC circuit. Okay, that works with our BaseSense 108 controls, but this is basically a 5-volt DC, and if this is wired in, it ignores all these other contacts. Okay. And anytime you're seeing 1 through 5, that's telling you have a 5-volt DC circuit. 1 and 2 is your zone temp, so you should be measuring probably about 2.5, 3 volts right here. If you're looking at the zone temperature. 2 is your common, and then 3 is going to be your cooling set point. 4 is your mode, which allows you to switch back and forth between heat and cool. And of course, 5 is going to be your heating set point. Now, if you don't use 2, 3, 4, or 5, and you just leave these first 2 wires hooked up, like it doesn't do it on here. First 2 wires, what it will do is it will fall to a default of 71 degrees heat, 74 degrees cool, and fan on. So if you just hang a 10K sensor on terminal 1 and 2 of this board, it will maintain that 71 degrees heat, 74 degrees cool forever. Which it's good for temporary operation. As you add the different inputs, it changes the way the thermostat controls the rooftop. But there's some logic built in that allows you to use just as small as a 2-wire control on everything up to a 50-ton unit, and these systems will run off of that. Now, if you go to the next set of wires, 7 through 14, this is a 32-volt DC circuit. So what this does is it allows you to have some information, some LED lights, or in the case of this thermostat, it'll give you some like cool fail, it'll give you a heat fail, system status, tell you if the fan's on, the fan's running. So 7, 8, 9, and 10 are basically information inputs to the thermostat. So, 6 is your common, 7 is a heat status, 8 is your cool status, 9 is your system, 10 is your service. The number 14 wires there just to make the display work on the control. So basically this thermostat works on 11 and 12, which is your common and your communication. And again, this is an all 32 volt DC circuit. If you see anything wired on these 7 through 14, that's what you're working with. You're working with this kind of control and a DC circuit. And again, when this is wired in, this terminal strip is deactivated. You can't, excuse me, you can't jump out R to Y or R to G and make the system run. You need to remove these wires to do that. And of course, when you get that's just standard wiring connection. So you can use any good quality thermostat, R to Y1, Y2, W1, W2, G. It's pretty standard. If you have a heat pump, you may have an emergency heat situation, but it's pretty standard connections when you get to the 24 volt. Excuse me. One thing I will say about the thermostats is they don't like power stealing thermostats. And I can pretty much guarantee if you try to put a Nest on this rooftop, it's not going to work. Nest thermostats tend to rob power, and if these controls don't work well, they will lock up and do all kinds of really strange things if you're not using a good commercial thermostat for them. So. All right, this is the old board, the UCP board, and it basically did the same thing that the new boards do, but the technology's changed a little bit. So with the old UCP board, we had to use this 1 through 20 terminal strip. And if you look at them on the older units, the 1 through 5 is still your 5 volt DC. That didn't change. And then the 6 through 14, again, is our 32 volt system. That really didn't change either. But what did change is the terminal strip got smaller, and 13, 14, and 15 is our compressor disable. So this is where you would wire in a frostat or something like that. So if you get on these units and these jumpers are gone and somebody has wires on here, that means that somebody's added a frostat, and that could be causing you some of your problems. 16 and 17 are your emergency stop. So again, make sure that if this jumper's not here, that that circuit is closed, because that shuts the whole unit down. Now, when we go into emergency stop, you're still going to see the light on the board. The light doesn't go out. We power the board from a couple different locations, and I'll get into that in a little bit. But this needs to be here. So make sure that this jumper's here or the wire's here and the circuit's closed. And make sure that if there are jumpers here, that all the screws are tight, they're not rusty or corroded or that kind of thing. Very seldom see, this would be for air proving switches, for air supply switches. And again, number 20 is your common on these older units. Test 1 and test 2, we'll get into this in a little while and explain how that works. And test 1 and test 2 has been on these rooftops since probably around 1990, 92, somewhere in there. And it really hasn't changed over the years. There are some things that are a little strange about it, which again, we'll talk about as we go. The new board on these units still has the test 1 and test 2 on the Reliatel units. And we only have 6 terminals here because we've put all the other terminals on the main board. So compressor disable is 1 to 2. Compressor 2 disable is 3 to 4. And again, emergency stop is going to be 5 to 6. So if you're looking at these, what you want to make sure is that, again, they're clean, they're not corroded, the screws are tight. If it looks like a capital E, all the letters are in place, okay? All the jumpers are in place. So make sure that you take a look at this if you're having issues or something's not working just right. Now, the old thermostats, these were 5 volt DC thermostats, and if you're working on them in the field, these are just potentiometer slides behind here, and think. No, we're not going to show a picture of them, but a lot of times these will get grease in them or dirt or dust in them, and a real simple thing to do is take some contact cleaner, get in there and clean that up, and these slides usually just start working. The nice thing about these old controls is if the slides fail and they stop working, is the unit usually just defaults to working off the sensor, and it'll maintain 71, 74. So if anything fails on here, it's a default back to standard operation on these rooftops. Now, to test these DC circuits, what you do is you grab a voltmeter, and if you go between pins 2 and 4, 2 and 4 is 2 is your common on these, and 4 is going to be your mode input. And in this case, if you read 0.942 volts DC, and you go to the chart in the book, in the Relitel book, 0.942 volts DC is right here. That tells us that the unit is in the off position and the fan is in the on position. So every one of these values means something different to the board. So if I turn the heat on and the fan on, I should read 3.68 volts. The board sees that voltage and it knows what to do. It's based on a DC voltage input. You can also measure the resistance to see if the control's working fine. So if I go between terminal 2 and 4 and I'm reading 7.69 k ohms or 7.69 k ohms, and I go to this chart, it's telling me the fan should be in the auto position and the fan switch should be in the auto position. So every one of these, again, has a resistance value that corresponds to the control. And you can troubleshoot the control or the system by using ohms or volts to diagnose it. The nice thing with this is you can do it from the rooftop. You don't have to be in the space to see what's going on. If you take these readings, you can do it right from the rooftop. Now, if you want to measure the heating set point, that's between terminal 2 and 5. Okay, again, 2 is common, 5 is going to be your heating input. And if I read, I'll jump back here, 2.358 volts DC, 2.35, let's see here, 2.358 volts DC is roughly in here. So you're looking at a temperature of roughly 50 to 51 degrees is what that's telling us. If I go to the cooling set point, like it shows here, and I read 2.327 volts on the chart, 2.32 volts, 2.327 is somewhere in here. Again, the thermostat is set for about 51 degrees, somewhere in that area. If I measure the zone temperature, the actual zone temperature, and again, that's terminal 1 and 2. And I read 2.52 volts on the zone temperature. If I go to the zone temperature chart, 2.52 volts is, it's over here, 2.52 is roughly 76 degrees is the actual space temperature. So you can, if you read the DC volts or the resistance value, you should be very close to this. If that space was 68 degrees and it was telling us it was 76, well, then we know we have a bad control. We need to replace that control. Okay, so, and that applies to the older stuff and the newer stuff. So if you're working on the old Voyagers or the new Voyagers, these voltages are the same. It applies to, stuff going back to around 1990, 92, somewhere in there. Now on the newer stuff on the Relitel, there's a couple different voltages that we need to look for. There's some reference voltage. And what we're doing on the Relitel stuff is we're using what's called Modbus communication. And the Modbus communication on J5.4 and J5.3 is ground. So J5 goes to your ignition module, and the 2 black wires are communication. So what you should see is about 10 volts, 10.2 what they have up here, 10.7, 9.6 to 10.7 volts DC. It's going to move around a little bit, but on the Modbus, what you're going to see is a 4-wire connector, and there's going to be 2 black wires, a blue and a red. The 2 black wires are your communication wires, and the blue is your common, the red is your 24-volt hot. So when we plug these boards in, we use the 24-volt hot and common to power the board, and then we measure our communication voltage on the Modbus, which are the 2 black wires. If you pull or disconnect the wires, you might see 10.5 to 11 or 11.2 volts DC. So there's some fluctuation there when you do unplug them. If you look at the wiring schematic on these boards, here's the ignition modules. Here's our LCI, which is our LAN talk communication interface. That if we had that in the system, again, here's our Modbus. So there's red and blue for power, and there's the 2 black wires for communication. There's our communication to, we gotta move this over, there we go, to the options module. So if we go from the Modbus to the options module, again, Modbus follows through. So the 2 black wires, the blue and the red, and it's always gonna be the same on all the Modbus communications. Here's our J5, which goes to the ignition module, or our J4, which goes to the communication bus, to the options module, and then eventually it goes back to the economizer. So it all kind of daisy changed through the system. Now, if I were to unplug the LCI or the LAN talk card and power the unit back up, the unit would see the cards not there and operate as a normal communication unit without this board in there, okay? So this is just, if you're looking at the wiring schematic, the Modbus is always the same. So that would be our train building management. All right, so, okay. So with that being said, there are some things we need to look for when we're checking voltages on the system. Again, there should be 24 volts on this connector right here. So you can always go from here to ground, and there should be 24 volts there on the old unit as well as the new unit. Okay. On the Relay Tub board, there's also some diagnostics built in. So we've got all of our communication. We've got our plugs. We gotta move this here. There we go. Okay, we've got all our plugs. Again, there's our 1 through 5. There's our 6 through 14. There's our WGY. Our main input here. This is going to be the main input for the board. And then we've got our J4s, our J5s, our other inputs for the boards. There are some diagnostics. So when you get to the rooftop, and if it's locked out and you're not sure what's going on, don't reset the power initially. Okay, what you want to do is go to this terminal strip right here. Even if there's wires on or if there's no wires on, whether it's a communication board, whether it's it's a train board or just a plain conventional thermostat, there are diagnostics available right here. Terminal 6 is going to be our common, 7 is going to be our heating diagnostic, and 8 is going to be our cooling diagnostic. So this is a 32-volt circuit, and if it's in a lockout, you're going to find some information here that's valuable when you're working on the board. So if I go to my heating diagnostic, which is terminal 6 and 7, and I see less than 1 volt DC, that means I don't have an active call for heating at that point. Okay, there should be nothing running if we're at less than 1 volt DC. Okay, if I go to this terminal and I see it's probably 28 to 32 volts, somewhere in that area. But if I see 28 to 32 volts DC, that's telling me I have an active call for heating at that point, and there should be something running. The system should be on at that point. If you go to that terminal and I'm seeing fluctuating voltage, if it's jumping up and down, if it's going 0 to 32, what that means is I'm in a heat fail, okay? And that's fluctuating 32 volts. and it's going to tell me I'm in a heat fail. And at that point, you're probably locked out. And the thing with these units is when they go into a heat fail, it shuts down the blower, the heating system. It locks the unit down. It's trying to protect the unit from overheating itself. And usually when you see that, it's TCO2 is open. You may have a zone sensor module if you have a heat pump. But usually it's a high limit trip, and if it trips 3 times on a call, it may go into a heat fail. If it's a flame rollout, it'll go into a heat fail. If your inducer pressure switch doesn't make, gas heat module failure, flame current sensed in the off state, flame current not sensed, but there are diagnostics on the ignition module, but typically in a heat fail, in my experience, 99% of the time, it's tripping the limit. And could be loose belts, could be dirty filters, could be plugged evaporator, it could be anything, you know, but it's typically a limit switch at that point. Now, the funny thing with these units is if the limit switch fails, initially it'll give you a heat fail, but when you reset the power, if the limit switch it doesn't reset itself, it's going to ignore the heating system completely, and it's not going to throw you any more codes. But when that happens in the test mode, it will just jump over the heating test. So if the high limit temp fails completely after you reset the power, you may not see that heating section. So it's got some quirks to it that you need to know about when you're working on them. Now on the cool diagnostics, so if you go between terminals 6 and 8, we have cool diagnostics here available, and it's kind of the same as the heating diagnostics. If it's less than 1 volt DC, that means that we don't have an active call for cooling. Okay. And this is just to show you that it's the same on the old units as the new units. But if I have 28 to 32 volts DC, that means I have an active call for cooling at that point. The unit should be running. Now, the compressor may not be running because that could be an economized mode. So even though it has an active call for cooling, doesn't mean the compressor will be on. If it's okay to economize, the economizer will be on. And we'll talk about economizers and how they work a little bit, because we're getting into the season right now where economizers are going to start working for us. If it's alternating, again, if it's alternating, and jump back here, if it's alternating between 0 and 32, 0 and 32, that means you're in a cool fail, okay? When you're in a cool fail, it could be, slide pod failure on the thermostat. It could be a zone sensor failure. But typically, it's contactor 1 or contactor, or the high pressure or low pressure switch is open. Now, it's also going to look for contactor 1 and contactor 2. And if those coils are bad, it will cause you some problems too. So when you're working on these, you probably want to ohm out the coil, the contactor coils, and they should be between probably 6 and 10 ohms resistance. If they're above that or below that, a lot of times the board won't recognize it. The amp draw won't be correct, and it will lock that circuit out. It does that to protect the contactor. So the contactor needs to be a certain value. But typically on a cool fail, it's going to be, again, high pressure switch or low pressure switch opening 4 consecutive compressor starts. So if that's the case, then we're looking at low charge, maybe restricted orifices, maybe loose belts, dirty filters, the usual stuff. So if you're in a cool fail, again, the contactor or the compressor is going to shut off, as well as the fan. The fan's going to shut down, lock down too. But again, if you go to those terminals and get that diagnostic, it'll kind of point you in the right direction. This is kind of a layout of a Reliatel system, and we talked about this earlier, but if you look at the transformer, we feed the board, we take 24 volts from the transformer, we go right to pin 1 on the board. So we feed that directly to the board. Now, pin 1 is always going to be the red wire. So if your light's not on the board, the first thing you probably want to do is go right here and check for voltage, see if the transformer is working. If I have power here and my light's not on the board, on the older boards you had a fuse that you could change. On the newer boards, it means the board's bad or you got a bad connection. So before you go too far into it, just look for power right here. But remember now, this power also goes. It feeds other things. It goes through the pressure switches and some of the safeties. It also feeds this low voltage terminal board. Okay, and it also feeds the number 12 pin here, which is our emergency stop. So we could drop this emergency stop out, drop power to this board. Nothing's going to run, but as you can see here, the light's still going to come on the main board. So just because the light is on doesn't mean that the phase monitors maybe not working. This emergency stop might be open. Check these different places for voltages. So if you have voltage here, and you have voltage here, lights on the board, and it's not running, it could be again emergency stop, could be phase monitor, could be almost anything. And this is just a little kind of a close-up of that to show that we do feed these boards from different locations. It's not just one wire feeds that main board. All right, so on the board, and here's that red wire right here. Okay, so as you can see, these pins are a little small too, so you're probably going to need needle points to get in there to get any kind of good voltage readings. But these are going to be your inputs and outputs. So there's your 24-volt hot and common to feed the board, and then you've got your pressure switch wires in here, your safety switch wires. You've got other circuits in here which we'll touch on later. But if you go to this last terminal right here, this is your outdoor air sensor. Okay, so if you want to read the outdoor sensor, and by the way, they do have the pins on the top here for your meters, but it still takes a fairly small lead to get in there. J8-2 is your outdoor sensor, and that should read somewhere between 2 and 4 volts DC. Okay. The thing with DC circuits to remember is that when we're working with a 5-volt DC circuit, if it's a dead short, it's going to show 0. It's going to short out, go to 0, and the circuit's going to shut down. If it's an open circuit, it's going to show 5 volts DC. So we should see somewhere between 1 and 4 typically. If you put your meter on there and you read 1.663 volts and you go into the book, it'll tell you what the outdoor temp is reading. So that's how you can test your outdoor sensor to make sure that it's reading the proper numbers. Now, if you were to take that sensor off here, pull the wire off, you should read 5 volts DC or 4.9, 4.99. And if you have the 5 volts DC here, that means the board is good. If you plug it in and it goes to 0, that means you got a shorted sensor. So there's good information just by taking some voltage readings here. The system will run without the outdoor sensor, but you lose some of your low ambient operation. You lose your economizer operation. There's certain things that outdoor sensor does for the unit that, again, it'll just run a little differently without it. One of the other things when you're doing startup or setup or even maintenance is make sure that the wire is on the proper tap. Again, the red wire goes on the common, and you move the blue wire from 240 to 208. If you move the red wire, it lets the smoke out of the control, okay? Always move the blue wire. What happens if you don't move the wire to the proper voltage? They come set for 240. If you put it on a 208 system, what's going to happen is you're going to have low voltage, 21, 22 volts. And since this board really looks for ground circuits and it looks for resistance values, it could throw things off and it may not work properly. It may give you some nuisance faults. So again, make sure you get the proper tap here for the proper voltage. And on a Voyager unit, you're going to have 2 transformers. You're going to have this control transformer, and then you're going to have a 350 VA transformer for the ignition system. And that 350 VA transformer has to be moved also. Otherwise, you're going to have Low voltage to your igniter may not ignite right. It's going to cause you some problems on that end of it. Now, um, on that 350 VA transformer for the ignition, all that does is that powers the inducer and the igniter, and that transformer is not powered unless there's a call for heat. So when you're looking at that transformer to see if it's working properly, there has to be a call for heat in order for that transformer to work. That's tied into the heating circuit. Okay, so that's kind of some basics. I'm just going to check, see if we have any questions in here, Bob. And oh, looks like we're good. So, all right. So I'm going to talk about coming in this time of year. We're going to talk about gas pressures and setup. The precedent's a little bit different than the Voyager. The Voyager is a negative pressure system, and the precedent is a positive pressure system. And we do have some minimums that we need for these systems to operate. So the minimum gas pressure coming into the unit needs to be 4.5 inches, while the unit's running. Maximum supply pressure, again, is 14 inches. If you get over a half a pound or 14 inches of pressure, what's going to happen is the valve may not open. So the valve is designed to open against that 14 inches. Anything over that, the valve may not open. It may lock itself up. Manifold pressure on a single stage should be 3.3 inches. And on the two-stage models, we should look at 3.5 on high fire and 1.8 on low fire. And this is for natural gas. So those are the pressures we're looking for when we're working with the precedent models or the YSC models. All right, so on LP gas, a little different animal. There is a specific LP kit for each unit. Minimum pressure 10 inches. And again, maximum is 14. We don't want to exceed that 14 inches on LP. When you're working with single stage units, the gas pressure should be set at 10 inches on high fire or on, for manifold pressure. On the two-stage units, we're looking for 10 inches on high and 4.6 on low. The 4.6 is really non-adjustable. So when you set the high pressure, the low pressure should follow it. I have not heard of any issues with it not doing that. I have had guys try to adjust the low fire, and you can get yourself some trouble if you do that, and it doesn't work just right. These things will soot up. And again, these kits consist of orifices and a high stage spring only. Some of the newer units actually have orifice plates in them. And if you run into that and you have questions, again, give us a call. So the heat exchanger is basically a tubular heat exchanger on the precedent. It's an in-shot negative pressure heat exchanger. The inducer draws the flue gases through it. And we've got, 3 different heat exchangers, a low, medium, and high heat exchanger, and they're not interchangeable. So and typically in the northern climates, we stock the high heat units. If you're looking for a low heat unit, you can't just change the gas pressure or change the orifices or the heat exchanger, because they physically are different units. So again, if you're putting a heat exchanger in there, make sure you get the low, medium, or high heat exchanger, and that's all designated in the model number. So now the other thing you remember on these units is there are turbulators on most units. Some of the newer stuff, they're changing the design a little bit. They're putting crimps in the heat exchanger. So I think at some point you'll probably see these turbulators disappear. But if you go on a job and you see the turbulators are discolored or they're pushing in like this, that needs to be corrected. Eventually what'll happen is they'll push in far enough that they'll start to crumble and fall apart, and then they tip the flame in a downward direction, and then they start to take the heat exchangers out. So when you're looking at these turbulators, they should be to the edge like this. This little stainless steel clip should be holding them in place. And if they're not, take them out, replace them, and make sure that they're in good condition so that we don't have any heat exchanger issues. On the precedent units, what we have is we have an inducer. Again, that pulls a negative on the heat exchanger. It exhausts out the side right here. On the precedent models, we have pressure switches to prove that the inducer is running. So the sequence of operation on these is pretty straightforward. It's just an 80% furnace. There's nothing really fancy about it. But the inducer pulls a negative on the heat exchanger. We close the pressure switch. On the precedent models, we have spark ignition and a flame sensor. And then we have a rollout, which is up here. And we have a temperature limit, which is down here, okay? So we run the inducer, we pull in the pressure switch, we start the spark ignition, and after, I think it's a 15-second pre-purge, the gas valve should energize, we should light the flame, and the flame sense should take over and sense flame at that point, okay? And this is kind of what it looks like if you haven't seen one. The one thing you'll notice is on these units, even if it's a single stage rooftop, we'll use a two-stage inducer. We just don't energize low speed. So, and that's the same on our 80% furnaces now. You'll see that these have two-stage inducers on them, but we don't always use the low stage. It's just for parts availability, it makes it a little easier. But this is our spark ignition right here. This is our flame sensor right here. Flame sensor depends on a ground, through the flame to the burner. So if you're having flame fail or flame sense issues, a few things you want to look for, of course, is make sure that this porcelain's not cracked or dirty. If you want to check the flame signal, what you have to do is pull the wire off here, put your microamp meter in series with this, and we're looking for about 2 to 4 microamps. And if you don't have that, what you want to look for, of course, is a rusty burner. Flame or the current can't pass through rust, so it has to have a clean burner. Also, what you're going to see on these systems is about 60 volts, 50 to 60 volts on this sensor right here. That's a reference voltage. So as soon as the flame comes on, we start to pass current through that flame to the face of the burner. And there should be 60 volts here. We should have the 2.5 microamps. Again, clean burners, make sure we got a good ground on the system. All of the simple little things that you look for when you're doing a maintenance on these units. We have 2 different boards for these units. There's a Relitel board and electromechanical board. So the Relitel board talks to the RTRM. The electromechanical is kind of standalone, and those are the only 2 different boards that we stock for these rooftops. Okay, and again, you're going to see on these boards, you'll see high and low inducer taps, and if it's a single stage unit, it's only going to use one of the taps on there. So boards are interchangeable from 1 and 2 stage, but not between Relitel and electromechanical. And that's pretty much it on the precedent. And again, if anybody has questions, give me a call, or see if I have anything in chat here real quick before we move on. Nope, looks like we're good. So next one we're going to talk about is Voyager. Voyager is a little different. If you haven't worked on them, this heat exchanger design has been around since the 90s. And on our models, the 3 through 25 ton, they set up pretty much identical. If you get into a bigger unit, some of the units actually have 2 heat exchangers in them. So if you get into the 30, 40, 50 ton units, this stuff will apply to it. It's just you're going to have double systems and double heat exchangers on some of the bigger equipment. So, but it basically works the same as the smaller equipment does too. So on these units, what you have is you have a drum type heat exchanger, and then this is a power burner. We actually pressurize the heat exchanger with this combustion motor, and we mix the gas and air in the combustion chamber right here. And then as it hits the burner cone or the burner, burner cone inside the unit, it fires off. So everything's pre-mixed inside this unit right here. okay? Now, when you look at the unit, there's different air holes. Depending on the size of the burner, you know, there might be 3, there might be 4, there might be 5 or 6 air holes in here. And again, it all depends on the size of the burner, but that's designed to get a proper mixture of gas air in this inducer and get it into the system so it burns properly, okay? Now, if you go on jobs and you see these holes taped off, usually what that means is somebody can't get the gas pressure set right, or there's an issue with the system that they can't get the gas air mixture. If you've got holes taped off, that means it's running too lean. They had to try to make the gas air mixture a little richer for it to burn properly. Don't want to leave them like that. We want to figure out what's going on. So if that's the case, take this manifold out. There's an orifice right inside here. Make sure this is clean. I've seen spiders in there and bugs, you know, bees, all kinds of things. The gas pressure won't change, but the volume does change. So make sure that this manifold is open. Make sure we're running the proper gas pressure. Make sure that the inducer is clean. Make sure that the back of the heat exchanger where the inducer sits, this little plate right here, there's a screen inside here. If that gets dirty, it's not going to work right. So there's a lot of things to look for if it's not burning properly. Okay, so what it does is it takes the gas air and mixes it in the combustion motor here, delivers it to this convex screen, stainless steel screen. The igniter is right here. The igniter lights off the gas air mixture, and the igniter also becomes our flame sensor. So it mixes it in the inducer. It's a negative pressure system. You have a 7-second trial for ignition, and you have 2 retries. So what's going to happen is you get 7-second trial for ignition. There's a 45-second warm-up on the igniter. So after that 45 seconds, it's your 7-second trial for ignition. If it doesn't light, it'll try 2 more times. If it doesn't light on the 3rd try, it'll go into a 1-hour soft lockout. And after 1 hour, it'll go to 3 tries again. So you could have a situation where you get a no heat call, and by the time you get there, the thing's running. It's just because of the retries after that 1-hour period. The combustion process, again, at the end of the 7-second trial for ignition, the flame sensor the igniter becomes the flame sensor. So this igniter has 110 volts to it while it's trying to light. Once it lights, it runs at about a 50 to 60 volt power to it, and it senses the flame in the unit, okay? And that's how we sense flame on these. Now, if you have too much gas pressure, it's going to lift off and it's going to get real loud. It's going to rumble when it lights. It's not going to start smooth. If your gas pressure is too low, it's going to pull it down closer to the burner, and it's going to make like a screeching sound. So you can usually tell if the gas pressure's up. If it's making a screeching or high pitched sound, it's probably low on gas, and if it's rumbling or lighting hard, it's probably, you know, high in gas pressure. One igniter fits all, which makes it nice for working on rooftops. So the kit 3033 fits every rooftop, every Voyager rooftop out there, the 3 through 50-ton units. If you got that on your truck, you got it pretty well covered. They're about 60 to 70 ohms when they're new. They draw about 3 amps when they're new. So if you want to check the amp draw, or if you want to check the ohm reading on them, if they're 150 ohms or more, you probably want to change it. If their amp draw drops off to less than 2 amps, you probably want to change it. So it's not that expensive. It's a good maintenance item. When we're dealing with manifold pressure, on natural gas, or for that matter, natural and LP, 7 inches is our optimal pressure for inlet pressure, and 0.2 negative is going to be our negative pressure. Now, when you start these units, what you're going to see is the gauge inducer come on, Let's see, what do I got here? Okay. So when you start these units, what you're going to see is you're going to see your gauge probably drive down to about 2.5 to 3 inches negative. And then when the gas valve energizes, it's going to come back to a 0.2 negative, and that's where you want to be. That's your optimal position. You do have a range in there of a 0.05 to a 0.35. So if you want to set it up and clean it up a little bit, you can adjust that 0.05 to 0.35 negative if you need to. But typically, the 0.2 negative is where you want to be. Okay. Natural and LP is the same pressure. So the only difference between natural and LP on these is the orifice. We changed the orifice on them. Otherwise, the gas pressures stay the same. They're negative 0.2 on all of them. This is an example of an overfired burner. It actually warped the back of it. Somebody tried to get it into a positive pressure, and it still ran for a couple weeks. But this is overheating. You don't want to do that. We have to stay in that negative pressure on these Voyager units. On the gas valve, or I should say for the flame sense on these units, since we don't have a flame sensor, it's on the board. And if you look on the board, there's a flame check, and then there's a V plus and a V minus. So if you put your meter on here on V plus and V minus, what it's going to do is it's going to convert microamps to DC volts, and it'll go from 2 to 4 microamps or 2 to 6 microamps, or in other words, 2 to 6 DC volts. We also have on the board, we have a LED, a red one and a green one. The green one is just your heartbeat to tell you if the system's in heat or standby. We have a couple of diagnostics. We have a 2-flash, which is a flame failure. We have a 4-flash, which is a limit, or a 5-flash, which is a gas valve circuit issue. We don't have a 3-flash on here because there's no pressure switch. All right, that was kind of a quick overview of the Voyager modulating, the Voyager unit. We also have a Voyager modulating system out there, and I'm not going to spend a lot of time on it, but I want you to know that if you run into a modulating unit, it's going to look a little different. It'll have a pressure switch and a VFD board, and then this is actually a 3-phase variable speed inducer motor or combustion motor. So the modulating is going to have a little different configuration. If you run into them, it's a little different animal. They actually run positive. They run a 0.02 positive pressure, and because of the pressure switch. One of the things on these units, if you look at it, the pressure switch is actually in line with the gas valve. So if that pressure switch doesn't close, it could throw a gas valve error. That's also tied in with the limit, so it could throw a limit error too. Again, it's a 2-to-1 turn down on ratio, and like I said, I wasn't going to spend a lot of time on it because we don't have a lot of them out there, to be honest with you. But if you do run into one, the temperature set point is controlled on the options module through this potentiometer right here. The modulating unit actually works with a discharge air sensor, and it modulates the blower or the burner up and down based on that temperature sensor, and then your set point is right here on the board. So again, modulating is a little different animal. If you run into them and you got questions, give me a call. And that's about all I'm going to spend with them. Why don't we take about 5 minutes and grab a cup of coffee or whatever, and then I'll continue on here. So I'll come back at 8 o'clock on the head. All right, guys? All right, so what I've got up here is the old Voyager terminal board. We're going to talk about the test 1 and test 2. And this has been on our units for a long time. A couple things to remember when you're in the test mode is that if the unit runs, it bypasses the communications, but it will never bypass a safety switch. So if you've got a low pressure switch open or a high pressure switch open or a bad contactor, it won't go into test. If the limits are open on the unit, it won't go into test. And a lot of times if the economizers have an issues, it'll actually lock out the test mode. So economizers are kind of the weak point of the rooftops where they take a beating. They're out in the weather, they get moisture on them. A bad economizer can cause you problems. Now, when you're on these units, you can isolate the economizer. On the old units, there's a 12-pin Molex up near the roof in the filter section. And on the new Modbus or the ReliTel systems, you can actually unplug the Modbus right from the economizer module. Or sometimes you can unplug J4 on the ReliTel board. You got to be kind of careful with the J4 because if it's a dehumidification unit, it will disable the options module and then the system won't run. So you got to kind of know what you got before you unplug the J4. But as far as test mode, again, it worked on the old as well as the new. And there's a couple of different ways you can do it. Now you can put a jumper on there and leave it there. And what it will do is it will put it in test mode and drive it through every 30 seconds. So test 1 is going to be fan, test 2 is going to be economized, then it's going to go compressor 1, compressor 2, then it's going to go to heat. It'll go to switchover valve if it's a dehumidification unit, but every 30 seconds it will drive it through if you leave your jumper on there. Now when you get to the end of the test sequence, if you leave your jumper on there, the board's just going to ignore it and go back to normal operation. It's just, you know, it's going to ignore it at that point. Now, if you turn the unit off at any given point during the test and turn the unit back on, it's going to ignore the jumper. If it sees a jumper on startup, it just ignores it and goes to normal operation. If you stop at any given point, so say I get to you know, step 3, I've got the compressor running. If I take the jumper off, it'll stay there for 1 hour. Okay, so that gives you time to do some diagnostics and look at different things. So anytime you take the jumper off at any given point, it'll stay there for 1 hour, and after an hour, it just goes back to normal operation. Now, the other thing you can do is you can drive it through quicker. You can just take your jumper and go test 1, test 2 for a couple seconds and then take it off. It should go into test mode. And then if you want to drive it to the next step, hit it again. You know, test 1, test 2 for a couple seconds. Take your jumper off and it should drive it through. So you can force it through a little quicker by doing that. When it's in test mode, one of the first things, I should have said this earlier, but when you put it in test mode, the first thing that happens is the light will start flashing on the main board. When the green light, or on the old one, the red light is flashing on the main board, that means it's in test mode, okay? When it's solid, that means we're back out of test mode. So there's a couple different ways that you can go into test mode. On the newer units, when you go to test 1, it's going to be fan, okay? Test 2, economize. Test 3 is cool, stage 1, stage 2, stage 3 if it's available. Reheat if it's a you know, a dehumidification unit, and then heating 1, heating 2. Now, everyone's a little different depending on the configuration. You know, if it's only a single compressor unit, you're only going to get, you know, 1 stage of test. But with some of the new units, and this will come into play when we're talking about fan setup, when you put these units in test mode, what happens on a lot of these new units is they only go to 50% airflow, okay? Economizer, they go to 50% airflow. Cool stage 1, they go to 82% airflow. So if you're trying to get something set up for like test and balance, don't just throw it into a test fan or even a G signal, because you're not going to get full airflow. Some of the newer units have different airflows based on what we're doing here. So again, those are the different test options. Now there's another way to do it. If you have a decade box or a resistor, if you put a resistor, say you take a 8.2 k ohm resistor and put it on test 1 and test 2, it'll go directly to cooling stage 3. Or if you put a 15 k resistor on there, it'll go directly to stage heat cooling, stage 2 heat. If you're doing maintenance and you want to carry a decade box, or if you got a resistor to put on there, you can put those on there and it will drive it there that much quicker. So things to remember when you're in the field. All right, we also have dehumidification rooftops, and basically what that is it has a evaporator and a condenser coil in front of the evaporator coil. So, and it has a switchover valve, a 3-way valve here. So when you go into dehumidification, what it does is it pumps through this condenser coil rather than this one. And this coil still is a little smaller than the evap coil, so it will net cool. I mean, it's going to start to cool, and they can actually overcool if you get into the right situation. So, you know, be aware of that. They pack a lot of stuff in there. And as you can see, the condenser coil is not as big as the evaporator coil, so it will still tend to overcool. You can use it two different ways. You can use a 24-volt humidistat or a 4 to 20 milliamp control, Trainer American Standard control. How do you know you have a dehumidification rooftop? You're probably going to have a lot of extra boards in here. So if you're using a Honeywell or just a set of normally open contacts, you'd go between pins 7 and 12. If you're using a milliamp control, you go between pin 18 and 19. So if you have these extra boards in here, that usually tells you that you have a dehumidification unit. You can check the dehumidification by taking a reading here. It'll tell you what the value is. So if I have 5 milliamps, I have 6.25% humidity, relative humidity. If I have 17, I have 81. So you can get a humidity reading if you're using a Trainer American Standard control. You can set the dehumidification units, this potentiometer right here. All the way counterclockwise is 40%, all the way clockwise is 60%. So you do have that range of 40 to 60%. You can read the signal here too, which is 0 to 2.5 volts DC to tell you where you're at. Couple things to remember, it's a cooling priority. So if it's in a cooling call, it's not going to go into hot gas reheat. The cooling call is going to take priority, and if it's under 40 or over 100, it's not going to dehumidify. So it's not if you need something to run in those colder climates or colder conditions, this probably isn't the right unit for you. Best use on these is convenience stores. That's where we see a lot of these go in. So that's the dehumidification unit. This is called the low bid. Okay, so we're going to talk a little bit about airflow because airflow setup's a little different on our units. So we're going to review belt drive airflow, and then we're going to take a look at some of the direct drive airflow. Now, in order to get the proper airflow, you've got to have a manometer. We've got to know what the static pressure is on the system. Electronic manometer, magnehelic, whatever you guys use is kind of up to you, whatever you're comfortable with. But taking a static pressure reading is really important. Now, when you look at, this is a 12.5 ton precedent rooftop. So when you look at the blower curve on these, it's like an eye chart. There's a lot of things to take in here, but a 12.5 ton unit, we need to get to 5,000 RPM, or excuse me, CFM. So in order to get there, we need to really kind of know what our static pressure is. If you look at the chart, anything under about a 0.3 static, we're looking at low static drive here. I mean, we don't need that blower doing a whole lot of work. It doesn't need to move all that fast. When we get a like 0.4 or above, now we're looking at the standard motor drive. So typically on a rooftop, if it's a 0.4 static, and we can take that all the way up to about, let's see, 1.2 static, we're looking at that standard drive, okay? Once I get above that 1.3 or 1.4, now I'm looking at a high static drive accessory, which is usually a pulley change. And if I get some really high statics, if I get up in this 2-inch range, now I might be looking at a 5-horse oversized motor to make that work, okay? So it all depends on the static on the system as to how we set these up. And that's kind of what this chart's telling us. So if you look at a Voyager, Voyager is pretty easy to get static pressure on. If you drill a hole in the blower door, excuse me, to get the return static, do it with the door open, don't drill into the tubing. But in this area right here, if you can get a static pressure in this area through the door, and then right underneath the burner, that's actually part of the plenum. If you drill in right here, you should be able to get a static pressure reading for the supply. So you can get your static. If you can't get it at the return ducts, you can do it from the rooftop. And those are the two places that you want to take a look at that. So we add them together. and look at a couple other things before we get into it. The factory sends that unit, so actually, factory sends all of our belt drive units set with the pulley open 3 turns. Okay, so on this 12.5-ton unit, 3 turns open means I've got 760 RPM. Okay, so if I look at my blower curve at a 0.6 static at 760 RPM, I'm moving 5,500 CFM of air. Actually, I'm moving too much air for that unit. Unless you're out west or in an area where you don't have to worry about sensible cooling or latent cooling, you're at 450 CFM per ton or 440 per ton, which is a little bit high for our market here. So what we want to do is we want to change that to get down to 5,000. And in order to do that, we have to take that pulley down to 720 RPM. And if you look at the performance data, 720 RPM means that pulley needs to be open 4 turns. So on a low static or a fairly normal static situation, you may actually have to slow down the blower from that 3 turns open to 4 turns open. If I wanted to go down, if I want to go lower, if I want to take down to 4,500, which is 682 RPM, I may want to take it to 5 turns open. And the only time you want to do that is if you're looking for better dehumidification. So now we're down to about 350 to 360 per ton. Just changes the dehumidification. But that's basically what this chart tells us. It gives us our static pressure. If we know our static pressure, we can look at our RPM. Our RPM tells us what the CFM is on that unit. So if I have a, and this is what we just talked about here, if I want to get to that 5,000 RPM, I have to be down to 720 RPM. And again, if I wanted to go to 440 per ton, 360 per ton, I'd go down to the 682. So that's basically what this chart's telling us is, what's our static pressure, what's our RPM, and that gives us our delivered airflow. There are ways to, there's a factory recommended way to make sure the belts are tight. And what it is take the distance between the pulleys and divide by 64. That's your amount of belt deflection. There is a gauge that you can buy to set that belt deflection, and it'll tell you whether you're close or not. I don't have one. I've never used one. The one thing that's bad about this is it says you need to check your belt tension at least 2 times during the first 3 days of operation. Then you and I both know you're not going back on the job 2 days later to go see what the belt's doing. So you give it a little extra tug, pull it tight, and the belt's going to loosen up a little bit over the next couple days anyway. If you're doing belt setup and you're not having issues right now, keep doing what you're doing. This is the factory recommended way of doing it, but I'm not going to change. If the guys got success with it, don't change what you're doing. And that's how you use your belt deflection. So the next one we're going to talk about is there's a unit called Plenum fan units, setting the airflow. And this is in our precedent models, okay? If you look at, there's some OSHA safety rules. The reason I put that picture in there was, Sean probably knows the guy there, but we put that in there because there are some safety rules you need to be aware of. So what Training American Standard has done is we've separated the high voltage and the low voltage, and we put a door on the high voltage side. Anytime you're working on something, I think it's over 200 volts, you're supposed to have hot gloves on, you're supposed to have safety glasses, arc shield, cotton clothing, standing on a rubber pad, all that kind of stuff. So, in order for us to help ensure that you guys are safe in the field, we put a door on the high voltage side, and we ask that you just take great caution and use your company's safety policies when you're in there working on the high voltage side of stuff. So Now on these units, we've got what we call a plenum fan. Okay, so a plenum fan is a backward curve fan, and it actually, if you look at this, it turns this fan turns counterclockwise. It paddles the air, it draws it in, but it paddles it. It's not like you'd think it would scoop the air. It paddles it. And again, these will operate up to 2 inches of static also. Um, but they're lighter. They're keeping the weights down in the units, and they move a fairly good amount of air at a pretty reasonable or pretty efficient way. It's on our 7.5, 8.5 high efficiency units and on all 10-ton models. Okay. Now, the other thing to remember on these is you cannot make them turn backwards. So even though these are on 3-phase units, you cannot make them turn backwards. They're auto-correcting. So don't use them to determine whether or not you've got the proper polarity on a rooftop. Use the compressor. We'll get into that a little bit too. But if you change the polarity on a 3-phase rooftop, it's still going to turn the same direction. It doesn't change. These fans don't change direction. And this just shows the side of the fan where it draws the air in. So currently, we're using 5 different motors. We're using belt drive, the standard belt drive. We're using some 5-tap direct drive motors. We're using some constant CFM, CTM motors. And what we're going to talk about here are the plenum fan motors. And the one for the electromechanical is slightly different than the one for the Reliatel. They set up just a little bit differently. And that's all based on the control. So on the original, the old stuff, we actually used something called the MMC board. That was the original. On the Reliatel models, we use an options module to control the speed. And the new electromechanical units, we're using actually it's an ECM board. And actually, this ECM, if you see it in there, it's going to be a little misleading. It's called the engine control module. Just how they named it. So it's called engine control. And as we talked about earlier, so when you're setting up airflow, remember we have some different airflows than we used to deal with in the past on these models. So ventilation is 50%, economize is 65. Cool 1 is going to be 65, cool 2 is 100, cool 3 is 100, and heat is always 100%. Because of UL and AGA regulations, anytime we're in heat stage, first stage or second stage, we're going to have 100% airflow in these units. So this is what's called the ECM, the engine control board. And I got a better picture coming up, but when you get into these, this is a set button here. So in order to get into these to program them, what you do is you hold this button for 3 seconds, and then there's a minus and a plus. So you can speed up or slow down the motor. And when you're done making your adjustment, you hold this button for 3 seconds again, and that remembers, or it saves your change, and then the programming is done. So it's pretty simple to use. The display on here usually comes set at 5.0, which is 5 volts DC. And on our units, you can go anywhere from 5 volts to 7.5 volts, and the speed of this motor will change based on that. So on the Reliatel models, what we're going to have is it's a potentiometer on the options module. Okay, and that's where we're going to set the airflow. And when you get to set these, there's actually a pigtail that hangs out down below here. And you put your voltmeter on there, set it to DC volts, and then you make your adjustments from here based on that voltage. And of course, on the old ones, the original ones, this just had a dial. You put your meter on here, you adjusted this from 5 to 7.5 volts DC, and you made your adjustments on this dial right here. This is no longer available, so when these fail in the field, you're actually going to get this module for replacement. There'll be a kit, and this module will replace that dial. So if you change any out there, you're going to get a kit to change that dial. So how do these work? It's basically the same curve here that you're looking at, but there's a little bit difference to it. So if we take our static pressure readings, and we look at DC volts, we can run these motors anywhere from 217 RPM all the way to 1700 RPM. They come programmed for terrain and American Standard at 5 to 7.5. So our range is going to be 1191 to 1700 based on the DC voltage. Okay. And how do we get there? Same thing, same process. We take a static pressure reading, and again, whatever gauge works for you. The precedent is a little bit different. So in order to get static pressure on a precedent, you have to get at the ductwork, or you can get to this plate on the end of the heat exchanger and drill a hole in here. Again, don't hit the heat exchanger. But if you drill a hole in here, that'll give you your supply static. And then on the return, if you get into this panel right here, same place, you know, in this compartment, drill a hole in that panel, you can get a return static on there too. So that you can get your supply and your return pretty easy, even on a precedent unit. So once you get your static, and again, when you're doing these units, make sure that we got it into this 100% fan mode. So make sure it wasn't at a cool, you know, it wasn't a fan call or a economizer test. It had to be in a cooling call or a heating call to get to that 100% airflow. So make sure that we're in that 100% airflow. And just for this example, on this 10-ton unit, they come factory set at 5 volts DC. So on a 10-ton unit, we need 4,000 CFM. And in order to get to that 4,000 CFM at a 0.5 static, we need to be at 1,435 RPM, okay? That's our target RPM. So on the unit comes set at 1196, our target is 1435. So if you look at this chart, I'm gonna back up here. If you look at this chart, 1435, well, 1432 is as close as I can get, is 6 volts DC. Again, if we left it at 5, we'd be at 1191. So what we want to do is we want to change that to 6 volts DC and get to 1432 RPM. And that's our target on that particular case. Now in this example, we're running an inch of static. Okay, so at an inch of static, 4,000 CFM for a 10-ton unit. Again, that's 400 CFM per ton. I want to get to 1,537 RPM. That's my target RPM, okay? And if you look at it, it gives you the brake horsepower that goes with it. I can't see it there, but it's, I think, 2.36 brake horsepower. But my target is 1537. So in order to get to that 1537, I need to go to 6.5 volts DC, okay? And what I do, I'm gonna jump past this one. What I do is I go into, if it's this control right here, what I do is I hit the set button and it'll display 5 volts DC, and I hit the plus button until it goes to 6.5 volts DC. Once I get to 6.5 DC, then I hit the set button again for 3 seconds, and that's made my changes. Blower should speed up, and you're all set. That's all there is to setting these motors up. If it's a Reliatel board, you want to adjust this potentiometer right here, and underneath the board, there's a yellow and a blue wire, 45G and 39G. What you do is you put your meter into this plug, this pigtail that's hanging down there, and adjust your motor to 6.5 volts. So go back to this potentiometer with your screwdriver and make an adjustment. When the meter reads 6.5 volts on these 2 pins, your blower's set. You should be all good to go, okay? Same thing on the old controller. If you need to get to 6.5 volts DC, you just turn that dial until you get to 6.5 volts DC on these 2, and you should be all set. Everything should be working at that point, okay? So what I want to jump back though is the nice thing with this is you can play with this a little bit. So say I want to dehumidify, I want to get to 3,600 at an inch of static. Well, I can run my blower at 1423. Or if I'm out west and I want more air, 1654. I can make that adjustment right here, and at 1432 I'm at 6 volts, and at 1633 I'm at 7 volts. So I've got some adjustment there. I can play with that. And it makes it a lot easier in the field to do some setup or some air balance. So, but that's the basic setup on the EBM motors. All right, I'm going to talk a little bit. Let me just check chat here, see if there's anything on. No, we're still good. So, okay. So I'm going to talk a little bit about economizers because we're in that season where economizers are going to be the big question right now. So we on the trained American Standard units, we have two different ways of operating our economizers. If it's a Reliatel system, we can use a 24-volt thermostat or a trained DC thermostat, and it makes a difference in the way the economizer operates. So what is an economizer? What are we looking at when we put an economizer on a system? First of all, the primary objective of an economizer is to take advantage of free cooling. If it's 50 or 55 degrees outside, let's take the outside air and use it to cool the building rather than bring on mechanical cooling. The secondary function is to try to maintain 50 to 55 degree mixed air. I mean, it's possible for it to be a 25, 30 degree day outside. If the load is big enough in the space, we could possibly be a combination of compressors and economize. It's all based on that mixed air sensor trying to maintain that 50 to 55 degree. We'll talk a little bit about the micro control units, although they're pretty much going away. Reliatel and the train dampers are the most current ones that we're using. So if you're using a trained thermostat, a DC voltage thermostat, it has the ability to see the space temperature down to 1/10 of a degree. And if you look at the way the economizer works, if the compressor will not turn on unless the space temp has not been reduced at a rate of 2/10 of a degree per minute over a 3-minute period. And the economizer has opened to 100%. So in other words, as long as it sees the economizer catching up on the space at that rate, it will compressors to come on, okay? Now, if you're using a conventional thermostat, what happens is when it's okay to economize, Y1 activates the economizer, okay? Even if it's a single compressor unit and you don't have a Y2, it will stay in economize forever, okay? So you don't have the ability to bring on that compressor unless you give it a Y2 call, okay? So when it's okay to economize, the economizer is going to energize, it's going to open, it's going to try to maintain that 55 degrees. And if it can do it and the economizer stays less than 100% open, it will not allow the second stage to come on or the compressor to come on. If we give it a Y2 call, it still needs to go to 100% open for 5 minutes before it will allow the compressor to come on. So in other words, you could have a Y1 and a Y2 call, and it could be an economize and the compressor is not coming on just because the economizer needs to go to 100% open for at least 5 minutes, and we have to not maintain that 55 degrees. Then it will allow that compressor to come on at that point. Where are the different the controls on here? The mixed air sensor is in the blower compartment. The outdoor sensor is in a couple different places. We'll talk about those in a minute here. But the mixed air sensor, some of the older units, there's actually a grommet in the back of the blower housing that it sticks in. Most of the newer ones are just clipped to the blower. The mixed air sensor on the older units is up inside this corner panel here. You have to kind of reach back in there and grab that and slip it out of its grommet. That's a duplicate. On the new units, the Reliatel, the mixed air sensor is down here by the foot of the compressor. And the old units, we don't use Honeywell anymore, but there was a Reliatel and there's an electromechanical unit. And that's kind of changing as we go. That's all changing, you know, in the transition of what's going on in the future here. So on these units, we used to have an A, B, C, D, and we added an F setting, or an E setting, I'm sorry. So now instead of 73 degrees as A and 63 as our lowest point, we can actually go down to 55 degrees. In our part of the country, you know, D and E is probably where we want to be for setup. If you're in a dry climate, you may want to be at 67, even 70. 70-degree air, if it's only 8% humidity, feels pretty darn good sometimes. So depends on what part of the country and as to where you're going to set this. We do have temperature readings for the sensors. So, you know, if it's 86 outside, you're going to see it's 8,000 ohms or 2.24 volts. So mixed air temperature, again, same thing. There's different values for the mixed air sensor. These are typically 10K at 70s, 77s. So if you know it's 77 degrees, they're going to be a 10K resistor. On the Economizer modules that we're using today, they've got fairly good diagnostics on them. You know, actuator faults, CO2 sensor. It really, these things really do tell you what's going on. You don't have to do a ton of troubleshooting. There are some input and outputs on this this control right here. So if this is if you're putting 2 volts in, you should get 2 volts out on your output on your feedback control. If you're getting 10 volts in, you should get 10 volts out. So in other words, these should match each other. If your input is 6 and you're only getting 2 as a feedback, you got something going on with the actuator. There's something wrong with the motor or the module. So, but then again, the diagnostics are pretty self-explanatory. So don't need to go into a whole ton of detail. If you see moisture on controls, change them. You know, there's probably an issue. Some of the old Honeywell electromechanical controls are replaced with this kit 16682. And it's basically a rewire. So if you run into these and you got to change them, I've done a few. They're a little bit over, they're a little bit much at the first time you do one, but give me a call if you get questions if you end up with these kits. So what I want to touch on now is how we set up the Economizer. If you look at it, they all look like this today. This is the electromechanical. This is the Reliatel Economizer. They're all kind of similar. Difference is on the electromechanical, we have a Y in and a Y out. Y1 in, one Y1 out, Y2 in, Y2 out. On the Reliatel, we don't. We have, it works off the Modbus. It's a communicating system. But the setup is basically the same on both of them. So if you look at this, we've got DCV, which is demand control ventilation. Here's our design. Design is our minimum position. So this is where you could set, when you give it a G call for outside air, you can set this anywhere from 0 to 100%. So counterclockwise is 0, fully clockwise is fully open. That's your minimum position set point. And here's your enthalpy set point. So you choose A, B, C, D, or E. Those are typically the only 2 you really have to touch on most applications. Now, if you get into DCV, which is, you know, demand control ventilation, that changes the game a little bit. The one thing you'll notice on here is we've got MAT, which is our mixed air temperature. Okay, that is the only input we really need. I mean, the outdoor sensor is part of the system, but we need the mixed air temperature. That's the one that goes on the blower housing. And that's what controls the modulation and the cooling call. We can add outdoor humidity. We can add outdoor temperature. We can add return air temperature, return air humidity. We can do averaging. But typically the only wires you're going to see on here are the MAT, mixed air temperature, okay? Or the Y in, Y out if it's a electromechanical system. Now, if you get into DCV, what you'll see is you'll see a plug on this pin right here, demand control ventilation, and it's a CO2 sensor in the space, and it's basically when you're in a situation where there's nobody in the building or nothing going on, you'll be at minimum position. As you add people to the space and the carbon dioxide levels rise, it will start to modulate the damper open. Okay, so DCV is you set your maximum damper position right here. So if your maximum damper position is 50% for your load for that building, that's where you set it here. And then you set your lower level and your upper level, okay? So lower level means that at 300 parts per million, the damper is going to be fully closed. And upper level means that at 500, it will be fully open. So what I do is I change this to say 1,000 and I change this to 2,000, just, for example. And what'll happen is when the room gets to 1,000 parts per million, it will start to drive that damper open, okay? And by the time it gets to 2,000 parts per million, the damper will be fully open or to that preset position, okay? So, and that's how demand control ventilation works. A lot of places are not using it at this point, but if this is connected, you're going to have to make some adjustments to these demand control ventilation points. The EXF set point, that's for your power exhaust. So if you have a power exhaust on this and you set this to 0, it'll probably run mostly all the time, anytime you get a call for fan or economize. Otherwise, if you set it to 50%, when the damper gets to 50% open, it'll bring on exhaust fans, power exhaust. And that's kind of basically how the economizer sets up. If you look at the Reliatel one, it's almost identical again, but you don't have that Y1 in and Y2 in input. Otherwise, they're pretty much identical setup. I'm not going to spend a lot of time on these because they're kind of fading away. We haven't used this control since 2000, so it's already 20 years since we've been using. There's a ton of them out there yet. The only thing I can tell you about these is if there's water damage on them and you're having problems, replace them because they need to be replaced. You can test them. There are some voltage testers if you want to put where is it here? Yeah, here. If you want to short CW to TR1, it should drive open, and CCW to TR1, it should drive closed, drive open. So there are a couple little tests, and again, I wasn't going to spend a lot of time on it because they're kind of fading away. All right, we do have phase monitors on all of our three-phase equipment, so don't get caught on that one. And basically what you have is you have a Y in and a common and a Y out. So this feeds the phase monitor and this feeds the system. That lets the power go through, feeds the system. And you either should have a green light or a red light. I have seen them with the green light on and the phase monitor is still not working, so don't trust that. Go here and take a voltage reading. Make sure you're getting 24 volts on this Y out. Here's your power, line 1, line 2, line 3. It's just monitoring power. Make sure you've got all three phases. Make sure they're phased properly. This is the internal connection to it. And again, we feed that by itself. We feed it from a separate circuit, okay? On a belt drive model, it's pretty easy. The motor turns with the direction of the vanes on the squirrel cage for checking rotation. Remember I said on the Plenum fan models, it's auto-correcting, so don't use the check for proper rotation. And make sure that you check the compressor, okay? When you fire these up, throw your gauges on there. If they're noisy and they're not pumping, they're running backwards, and they won't run long like that. But the best way to check them is to just put your gauges on there, make sure we're pumping, make sure they sound like they're working properly. Listen to the scroll. On a three-phase system, reverse any 2 wires, and you've reversed the rotation of the compressor or the system in general. So make sure that if you're going to change rotation, you switch any 2 of the wires. One of the things I want to talk about is voltage imbalance. It's important on the system. When you're running these systems, if you do a startup, make sure you check the voltage, check the amp draw. It gives you, it leads to inefficient operation, overheating, failed compressors. It can cause you all kinds of problems, and it for the little bit it takes you to do it. It's something that's very, very important. Oh, back up here. Okay, so if you look at this, and I don't have the sheet up here, but this is how we do it. We check, A to B, B to C, and then A to C. Make sure we, check our voltage, add them up, divide them by 3 for our average voltage, and then take our deviation to the farthest voltage, and that's our percent of imbalance. In this case, it's 1.7. I got a couple examples here that we're going to talk about. So in other words, go A to B, or line 1 to line 2, line 2 to 3, line 1 to 3. Make sure we're 2% or less. One of the reasons that that's very important is winding resistance. I thought I had the sheet up here, but I don't. If you're within that 2%, your windings are going to run at a certain temperature. So for every 1% that you're over, if you're at 3%, your windings are going to heat up by 8 degrees. So if you're off 4%, you're going to get 16 degrees. You're going to start to overheat this, and you're going to start to lose compressors. So if you're losing compressors and you don't know why, this could be the whole reason. So basically what we do is we take our voltages, we average them out, divide them by 3, take the farthest deviation. In this case, 623, or excuse me, we got an average of 208, and the farthest deviation is 204. We have an imbalance percentage of 1.5%, which is perfectly acceptable. Okay. In this case, we add voltages up. We divide by 3, take our average, the farthest deviation. So 226 divided by 221. And my imbalance is 2.2%. This is not acceptable. This has to be corrected. Okay. Couple things is make sure the wire is the proper size. Make sure that the connections are tight. There's no burned connections. The contactors are good. Check the basic stuff that you can check, and then call an electrician or get your local utility in, because if you need to change the balance on a system, you have to start moving breakers and doing things that you probably shouldn't be involved in. So once you identify the problem and you've looked at the basic things, just move on and let the electrician jump in at that point. Let them get it corrected. So I've seen them as far off as 3, 4, 5%. And you know what? On a 3D or 6D compressor, that can cause you some huge issues. So make sure that voltage and that amperage balance is where it needs to be. All right, last thing I got on here is meter leads. If you guys need needle points, it's probably a good thing to have, not just for our equipment, but if you're working on Mitsubishi or just about anything these days. It's a great investment. We sell them if needed. Last thing is startup sheets. You guys are having problems in the field, do a startup sheet. We have precedent logs, we have Voyager logs. If you need these, let me know. I can email them out to you. But by the time you get down through the voltage and the amperage and the subcool and superheats, usually you can tell what's going on with the system. But do a proper startup, and keep them in your file, and make your life a whole lot simpler. So that's it, guys. I know we covered a lot this morning, but if anybody has questions, email me. Let me check chat here quick, see if anybody's got anything. or get a hold of me directly. And if we don't have anything else, guys, I appreciate your time this morning. Thanks for dropping in.